In the vast and intricate world of calculus, integrals stand as powerful tools that enable us to solve problems that initially seem insurmountable. From calculating the area under a curve to determining the volume of irregular solids, integrals provide a systematic approach to unraveling complex mathematical relationships. This comprehensive guide will serve as your compass as we navigate the fundamental concepts of integrals, equipping you with the knowledge and skills to conquer even the most challenging integration problems. Whether you are a student grappling with calculus for the first time, or a seasoned mathematician seeking to refresh your understanding, this guide will provide you with a clear and concise roadmap to mastering integrals. We will embark on this journey by exploring the very essence of an integral, delving into its definition and understanding its significance in the broader context of calculus. Join me as we unlock the power of integrals and uncover the elegance and beauty that lie within this fundamental concept of mathematics. At its core, an integral can be understood as the reverse process of differentiation. Just as differentiation allows us to find the rate of change of a function, integration enables us to determine the original function given its derivative. In essence, integration is the art of finding the antiderivative. Imagine a curve representing a function. The integral of that function would allow us to calculate the area enclosed by the curve and the x-axis. This area represents the accumulated value of the function over a given interval. For instance, if the function represents the velocity of an object over time, its integral would give us the total displacement of the object during that time period. To represent an integral mathematically, we use the integral symbol, which resembles an elongated S. The function to be integrated is placed after the integral symbol, and the variable with respect to which we are integrating is indicated by dx at the end of the expression. In the upcoming sections, we will delve into different types of integrals and explore various techniques for evaluating them. Get ready to unlock a world of mathematical possibilities as we dive deeper into the realm of integrals. Integrals can be broadly classified into two main categories: definite integrals and indefinite integrals. Understanding the distinction between these two types is crucial for mastering the art of integration. Definite integrals are those that have specific limits of integration. These limits define the interval over which we are calculating the area under the curve. The result of a definite integral is a numerical value that represents the exact area enclosed within the specified bounds. Indefinite integrals, on the other hand, do not have any limits of integration. Instead of calculating a specific area, indefinite integrals provide us with a general expression for the antiderivative of the function. This antiderivative represents a family of functions that differ only by a constant term. To illustrate the difference, let's consider an example. Suppose we want to find the integral of the function f of x equals 2x. The definite integral of f of x from 1 to 3 would be written as the integral from 1 to 3 of 2x dx. This would give us the area under the curve of y equals 2x between the points x equals 1 and x equals 3. The indefinite integral of f of x would be written as the integral of 2x dx. This would give us a general expression for the antiderivative of 2x, which is x squared plus c, where c is an arbitrary constant of integration. The power rule stands as one of the most fundamental rules in integration. It provides us with a straightforward method for finding the integral of functions that involve powers of x. The power rule states that the integral of x to the n is equal to x to the n plus 1 divided by n plus 1 plus c, where n is any real number except for -1. To understand how the power rule works, let's consider an example. Suppose we want to find the integral of x squared. Applying the power rule, we add 1 to the exponent, 2 plus 1 equals 3, and divide the term by the new exponent, 3. This gives us x cubed divided by 3. Finally, we add the constant of integration c to obtain the complete solution. The integral of x squared dx equals x cubed divided by 3 plus c. The power rule can be applied to a wide range of functions, including those with negative and fractional exponents. For instance, the integral of x to the -2 can be found using the power rule as follows. The integral of x to the -2 dx equals x to the -2 plus 1 divided by -2 plus 1 plus c, which simplifies to -x to the -1 plus c, or -1 over x plus c. In the next section, we will explore another important integration technique known as substitution, which allows us to handle more complex integrals involving composite functions.